about bifurcation right now, so.
Yeah, well, bifurcations are like a broken symmetry, but it's kind of like I think a little bit further along than just a bifurcation. A bifurcation is known in chaos theory, in the mathematics of catastrophe theory too, I think. But a broken symmetry, you have to do the physics of finding the symmetries that are fundamental for a certain set of entities, and then you can only define the broken symmetry. So it's defined quite a different way than catastrophe. You might also look at phase transitions and states. Phase transitions I see within an emergent level in a set of entities, but they have a shift from one thing to another. So there's a kind of a somewhat of a similarity between phase transitions and broken symmetry, but not really. They're fundamentally different in my humble opinion. In one of my other messages, I said, I keep saying in my humble opinion, and I hope you forgive me.
Because we know it's not.
Yeah, it's not presented, it's ex cathedra statements, really. I'm more religious than you think. Is Peter joining us? I guess not. He doesn't join these.
Not generally. He has an open invitation, but he doesn't attend.
He has several others that he
yes.
Less serious people than this group.
Yeah.
I call you the integration squad, and I just looked it up. What is the squad in the Army? It's 6 to 10 people. The most intimate group of people who fight together, and that's us.
Yeah, yes. Normally we're fighting other people, not within the team.
Us and them.
The first time I saw Len use the word squad, I said, "Oh, I kind of like that." I don't, there's militaristic leanings, and I was, but the size fits. It's kind of a, yeah. It also has a purpose. It's not just a clan or something, or it's not just a coffee club, or I don't know.
Back about 40 years
the
ago,
integration coffee club. Yeah.
Yeah, that's true too. I guess we kind of rely on each other, and we have each other's backs more like a squad. So it's not the militaristic so much, it's we're a band of brothers, so to speak, and sisters, I must say. But we're not a tribe, we're not a genetic
it's not big enough. It's not big enough for a tribe.
Yeah, that's true.
IIS might be a tribe of some kind.
Tyler, I've actually adopted one of your levels, the Ag Village, before the city. I keep multiplying my
good
levels.
Origin of agriculture is important. Yes.
Oh, absolutely.
Separately from the state. Separate from the state. Yep. Earlier. Mm-hmm.
There was a recent Nature Science that had worms on its cover, and I decided to do an origin of soils because that's so important.
Okay, so I think we can start then. So as per last time, I want to give everybody the chance to talk and present if they have something that they would particularly like to share. But we've had some, I think, some important inputs from Hilary and Len. So I would like to start there, and I think it would be useful for Len to explain what he has in mind in terms of isomorphies and what they mean, because I think that I certainly had a maybe a slightly different understanding of what Len meant. So I'd really like to get a better appreciation for what Len thinks they are, and how they might be used.
Okay, I'll start, but I'll be brief because most everything is in that message I just sent to you, and so I'll rely on that email. But remember when we talked about hierarchies, I talked about one level giving rise to the next, but then once that is established, that's where the isomorphies come in. It sustains those levels. It's not the emergent isomorphies. Those are that short list I gave you. And after the emergence, there's also subspecialization. So we kind of define our hierarchies in terms of this rather than this in the past. When we've examined phenomena, we've done reductionism and decomposition by reductionism, and it's been very fruitful. And so I want to emphasize, I think Hillary did a brilliant job of causing me to make that distinction. I had never made it before, but it's very important distinction that once the emergent level happens, then we have a whole series of phenomena in nature, which we studied with the sciences in great detail and by armies and armies of scientists of different disciplines. And by them bringing forth evidence and facts about the various phenomena, we could compare them afterwards. And that list of candidate isomorphies really came from comparing those and looking for at them. And as Luke has said in the past, Luke's not in this group either, but I use his name often. He understood that it's the identifying features and functions that have to be tested on each level to say whether they're truly isomorphic or not. And I've added to features and functions to features, I've added measures, because certain of the sciences have been able to measure certain of the things which are in, or sometimes they put formulas on them. I could actually expand identifying features and functions, but it's whether all of them have those identifying features that makes them an isomorphy, in my humble opinion, again. Or ex cathedra statement is. Go ahead, Gary.
Can I just ask a question to try and unpick this in? Well, not
absolutely,
but to get to. So in your unbroken sequence of origins, you show a wave. Yeah.
Yeah.
Now, are you saying that what your classic isomorphies are at the peak? Where
they're in that upper part of the wave, right?
Okay. Yeah.
Within a level.
Yeah. So integration and differentiation or diversification, you don't consider those, do you consider those isomorphies?
Well, I have included variation. And in fact, I think it was Tyler Volk who challenged me once and said, I just don't quite understand the fragmentation or the diversification step. And so, Tyler, what I did in my humble wisdom is I made a long hierarchical list of all of the peripheral instabilities on the genetic level. I included the central stabilities too, because the genetic level, since I taught genetics for 40 years or so, I kept up with in the literature. And I could, from the top of my head, I could develop a list of 4 or 5 pages of central stabilities that gave rise to instabilities. For example, when you look at the DNA sequence, there's a whole series of, you might say, repeating processes by which the sequence is changed. Or if you look at chromosomes, chromosomes were an attempt by organisms to conserve the genetic information. But as soon as you got chromosomes, you got ways to change the chromosomes, like crossover and so on, which then added to the variation. So my hypothesis is, at least for the genetic levels that I developed for you, and because of your question, is that the peripheral instabilities actually develop after the central stabilities have occurred. In other words, the fragmentation occurs after the you might say, stabilization or sustainability. Helene wants to.
Yeah, I have a question. Could you say that the fragmentation or the diversification is actually the instances of the original isomorphy that arise in their own domains or milieus or whatever, and so they start from common features, but then they spread out because they take different traits. So let's say you can, I mean, if I want to do some
Yes, that one.
That one?
Yes.
Anthropomorphic metaphor, I'd say that you have language. I mean, it's not an isomorphy, but, and then you have language as a quality or as a function, but then you have different languages diversifying.
Exactly. In fact, I have a level in the USSO, which is Origin of Languages.
Yeah, but
origin of
and
brain.
it happens for many different. It happens for many different forms,
Yeah.
let's say. And so my comment, listening to many discussions that are going on systems literacy or integration, etc., is that we find ourselves, and so it's just to put this as a, you know, as a reminder to address this at some point, and this is what probably I'm addressing more than anything else, is that what you have to notice, what actually is there for scientists or whoever to observe and notice is the instance and not necessarily the original form. And so we're in a situation where we're almost in like circular references unresolved, that we want to find the shared form in order to explain the connection of the diverse elements, but we can't find it before we study the commonality of the different instances of the forms. And I think this is one of the hard nuts to crack, because, and I just had a discussion with Peter a little bit earlier, that we're talking about systems literacy and what are the abstract features of a system, but we actually only see the features of a system when we actually study an actual system. And so how do we relate the actual observed instance to a more abstract element? I just wanted to relate this in the context of what you were saying, Len.
Well, I think it fits very well. I mean, imagine in your mind a tree, and Scientific American has some excellent summary articles on this, a tree of all the languages and their diversification from each other. As you go back in the tree, you see branches of the extant languages, but then they cluster together into main branches and then into the trunk. And that's the commonality you're saying. You have to look at the diversification in order to find the commonality and then construct these trees post facto, you might say, going back in time. And they are, the example of languages is very close to the example of genetics and the various forms of genetics that I'm saying. So I perhaps have used up my time now. We should go to Hillary, but I compliment Hillary on his wanting to test and falsify thing. But Tyler first has a comment.
Yeah, I really look forward to Hillary too. Thanks, Hillary, for setting that out. So Len, these I am very interested. We probably won't have full time today in your isomorphies that you think more directly relate to the unbroken sequence, this counter parity, broken symmetry, central stability, peripheral. There's this list of 8 or 7 that you sent out today. Concrescence, I think we in a way we've been talking about the merging related to George's ontogenesis, but I wonder, I don't think we maybe have time to go through all of them, but could you just say a word about, for example, a broken symmetry, and like an example from the physical chemical realm, an example from the biological realm, an example from the human realm, of a cultural realm. Like
Jennifer Naker, as you know, is our new managing director, and after listening to my USSO, she said she crucified me. She nailed me to the wall essentially with her first question was, okay, so show me counter parities on each level. And that's the essence of the whole thing.
Well, yeah, I would. Yeah, that's what I would like to see.
Okay, I want to tell you right off, Tyler, that broken symmetry is an impulse and an intuition of mine. It's not very well developed. When I gave some talks at the University of Alaska in Anchorage, I met a guy in one of the small colleges who wrote a series of papers on broken symmetry. And if you look it up, people will talk about broken symmetries in chemistry and physics and in biology, but I haven't looked at those yet. So my hunch is, my intuition is that there's broken symmetries that are associated with the counter parities. And that's just a hunch right now. And
well, just to take one example, so you're an expert in the eukaryotic cell evolution. So what would be? I mean, broken symmetry comes in the separate. My knowledge, it comes in the separation of fundamental forces. As electromagnetism got separated from the weak force, there's something they call broken symmetry there. I'm not really familiar with the term in biology. Well, there is when the sperm goes into the egg, like a frog egg, it does something about setting up a meridian of. I mean, I think it's in embryology. It does come into play how a sphere turns into a bilateral thing. I'm just sort of making this up, but I guess I see concrescence. I definitely see some of those terms. I almost can immediately start seeing them in the unbroken sequence or ontogenesis, but I just was wondering how broken symmetry fits into, let's say, the prokaryote to eukaryote merger. So you're treating these as hypotheses at this point. You're
right.
Not claiming you have answers for these questions at this point.
No, I don't. I just am not ready to give an answer on broken symmetries. It's just a hunch of mine right now.
Okay.
And perhaps broken symmetries are related to the counter parities. It just seems to me that when an emergent event, the big E event happens, it breaks some symmetry that was in the past, and that is the new counter parity that emerges, which gives rise to a whole new set of entities at a new scalar level. But I haven't pursued that yet, and I apologize, but broken symmetry is a little bit like the gap that's between the emergent levels, which I'm no longer a big advocate of, as a matter of fact, because I've lived for 50 years and well, I lived for a lot more than 50 years, but I've been studying these things for 50 years. And even in the astronomical realm, I keep finding intermediate things that were comfortably missed 50 years ago when people did the original work on the gaps in the astronomical hierarchy. I mean, look at planetesimals and moons and asteroids and comets as intermediate between planets and brown dwarfs and stars. I mean, now there just seems to be a lot more stuff in the gap in between, so I'm not as confident of either the gap or the broken symmetry in between.
Thanks.
but I'm still going to pursue it.
Okay.
Like you and I should both read that article that I have in all those 4,000 or so I sent you, that literally talks about broken symmetry across those three disciplines I just mentioned. And we should, you know, take up that issue as a separate thing when we get to it. Right now, counter parity is the way I described the emergence of a new level. And even that one, I only have counter parities on the most physical levels, like chemistry and compounds and things like that, and protein interactions. The counter parity is very obvious there, but it's a lot harder to find for the other levels. But it must be found if the theory of emergence is going to emerge as something useful. And I confess right now that that's one of the things I have to do after all these other things I have to do. Right now, I'm just setting up the research underpinning, as Hillary has pointed out. It's just the beginning. And of course, a lot of people in the world will not even accept meta-hypotheses. I know my reductionist friends won't in cell biology, because I've done it before, and they crucified me immediately at a meeting.
So how long ago was
shouted
that?
Down.
How long ago was that then?
Oh, that was at the very beginning of my professional life in 1972 or so.
Oh, that's
That's a long time ago. What's happened since then? They might have changed. They might be more persuadable.
Well, I don't think so, because they're very reductionist, you know. We can't go to the reductionists to do these sorts of things because they won't look beyond their reduction. In fact, they're incapable of it. Even the systems engineers who are supposed to be engineers who are systems oriented can't go beyond their original. I remember a meeting at the International Workshop when I first introduced feedback across all the levels. And oh, there was an uproar from the engineers because it didn't follow the problems that they had done in Sham's outline series on feedback for one of their courses.
Oh, Len, but things have changed because every time, I mean, 15, 20 years ago when we were first looking up isomorphies and trying to track them down, we had, oh, sure, a few were written about, you know, tipping points, and a few things, chaos, the book had been written, and a few were sort of obvious. A bunch were not. So we had to go mine for them in the journals. Now, every single issue of Nature and Science, you open them up and somebody is writing about networks and comparing it to networks and stars, you know, because they're writing about networks and ponds. I mean, every single issue has at least 3 or 4 articles based on network theory or chaos theory, or not often chaos theory, or some kind of isomorphic base. It's common in the literature, and it's how scientists are thinking out there, especially ecology. Thank you, has done that. Climate change, all of that is working in that way. Now it's so easy to call something an isomorphy and find it. Before we had to mine for it, and it was called different things in different sciences. Now it's just right there. I mean, right there. All I have to do is type it in. And for most things, they're just sitting right there in Wikipedia and right in the literature. It's just not that hard. There are, of course, in your long list of isomorphies, that are many that aren't there or are still disguised. But generally, the big ones are right there, right in our faces, and being commonly used.
If I may, I'd like to show one of Len's diagrams, and again use that to try and get some clarity, even if it's just for me to understand. So I'll just show it this quickly. It'll only take a moment, I think. So this is your diagram from all of your previous works. Now, I think what you were explaining to me earlier is that you have a number of isomorphies related to sustainment or involved in the sustainment of the system. Yeah, at the peak. Yeah, and I know that you also have isomorphies relate, you know, what you call pathologies, I think, processes of decline and you know, dysfunction perhaps. You know, so if we have a system which is in place and created here, then is there a path of decline going you know, on, you know, going away from this?
Well, Gary, let me react to your borrowing of the diagram and putting your own labels on it. I agree with isomorphisms of creation, which I would call emergence, and isomorphisms of sustainment. I definitely agree with those, but I do not agree with isomorphisms of decline or pathologies. It's not because of pathologies that you go down to the variation, but actually because of the sustaining things.
Yeah, that's why I didn't show it coming down here. I've only just done this. I've done this, you know, while we were talking, based on. Oh,
you did?
Yeah, no, I was just trying to understand that, you know, this is my thinking currently. Yeah, and apologies if this is completely wrong. And I was wondering if you have in mind isomorphies of diversification as well. You know, are there isomorphies here? You know, are these all isomorphies, or different types of isomorphies? I don't know. I'm just trying to find out what you think, Len, to be honest.
Well, all I can do is give my initial reactions from my experience, and I haven't looked at isomorphisms of diversification per se as a title, but that's a possibility. I haven't divided them up that way. And I would disagree with the pathologies, because although the curve comes down, and it's easy to associate that with decline, it's not decline that leads to
that's why
senescence.
Yeah, that's why I didn't show it here. It's sort of there.
It is. It is sort of there, because as soon as you have a wealth of sustainability, then you have the possibilities of senescence within it. It's also, in other words, a follow-up on the sustainability and the wealth, I think. But I wouldn't associate those with the decline. In fact, the fragmentation branches are built on the sustainability itself, as I was pointing out. But the pathologies are, in fact, isomorphic also. But I just, it's interesting that you modified the diagram just in our discussion. So a lot of it, 2/3 of it, I certainly agree with.
Okay. I just think, I mean, when we come on to, you know, Hilary's and then later when we talk about, you know, what do we do to test, build, you know, organize the isomorphies, maybe something like this might be helpful as well.
Oh yes, because it classifies them in terms of their function. I want to say, while I have a rapt squad audience, that one of the things that impresses me the most in systems approaches, and now I've lost my thought, so I can't state it. Sorry, I lost it completely.
Maybe it'll come back.
Yeah.
Okay. So, do anyone else have any comments on what we've been discussing so far before we move on to Hilary's proposal?
If there's time toward the end, I definitely have a few things.
Great. Okay. Does anyone already have in mind something that they would like to share, just so we can take that into account in the agenda? Tyler, Lynn, Helen.
We've lost Helene in terms of pictures.
I've got her.
Oh, it's just my selection, apparently.
Yeah.
I see George now, though.
Yeah, if you go into gallery view, you should be able to see all of this.
Oh, I have just too many on the. Yeah, I see Helene now.
Okay. Right, Hilary.
Okay. Let's see.
Tell us more about your proposal.
Yeah. I tried to share my screen. It failed. Post disabled screen sharing. Right. Okay, that's fine. I won't share.
Okay, go. See if that will work now. It looks like I have to proactively allow sharing, whereas it used to be.
Okay, that's fair enough.
Great.
Okay, so what? Why is that doing that? Right, so can you, if I go on to presentation view, will it show it or not? Will you see it? Well, one way to find out.
Give it a try.
Yep, I did. Right, are you?
Yeah.
You see that?
Can still see. Yeah.
Okay, so I guess this is this is a slide I did probably about a year or two ago. And the background to this is the IFSR conversation in, was it 2018? When George and I met, and George was enthusiastically recommending Tyler's book and Morowitz's, and in Cozy Fellows Systems Definition project, which I was leading, and we're just trying to wrap up, there was this huge disconnect between the constructivist worldview and the realist worldview. And we eventually managed to get a formula that says actually it's both and, which effectively is just Rosen's modeling relation. You've got models of systems and you've got real systems. And that's the way I see it, but from reading John Kinnaman, I see I'm taking a far too simplified view. So the reason that I particularly liked Tyler's grand sequence was that if you read Allen and Starr's book in Hierarchy, they say that this is all in the mind. That the realist view of systems doesn't work. It can't work. It's impossible. And I thought, well, that's rubbish. But how do you prove it? And similarly, Erik Aslikson is a staunch constructivist. Unless a system is an object, it can't possibly exist. So, well, if it's a system, maybe system is a different meta type than object. Maybe even an object is only one kind of system. And the critical point, the other aspect of the argument among the fellows was people like Derek Hitchens saying it's not a system unless it's got people in it. And that leaves you in a bit of trouble when you start designing autonomous systems that behave as if they had human operators inside them. And it just doesn't make any sense. But because I'm a disciple of Eric's, I spent quite a lot of time trying to connect his view to other people's views, and eventually decided, well, no. So we ended up with a fairly simple definition of system, and the realist constructivist thing we kind of fudged by saying, well, it's both. But then thinking this through, if we can, as Tyler has done at least qualitatively, and Len has done in much more detail, more rigorously perhaps, but I don't want to go there. I think they're both incredibly valuable bits of work, and complementary in the way that I'll try and describe. You go from here to here to here to here to here. You've got exactly the same big E emergence process jumping each level, and then the spreading out, and then somewhere there you get another jump up to the next level, and then it spreads out. So you've now got a scientifically verifiable evidence trace all the way from geopolitical states down to quanta. And I'm not quite sure whether that's a system made up of smaller things. Sorry, it should be quarks, not quanta. But I'm not sure whether you've got a level below or whether this is actually a fundamental particle. We all thought they were fundamental particles quite a long time ago. In fact, I think when I was at school, we thought that nucleons, or at least we were told that nucleons were fundamental particles, but maybe they were lying. So one of the things that was intriguing us at the time was how does this play into the different disciplines? And another was, what are the common isomorphs all the way up, and where do you start getting changes? One of the things we noticed is Tyler's phrase, which I love, of a system in energy repose. That's these kind of bottom physics and chemistry ones. And then we move up to systems that actually are high energy, that need a continuous flow through of energy to maintain a very high entropy differential with the rest of the universe. We then get to, well, animal or, yes, so Tyler calls them animal social groups. Now, I know we've had a big argument about this before. I maintain that this includes very simple human extended family groups way back in hunter-gatherer times. And these, of course, coalesce or can communicate with other similar groups into human tribal metagroups. And there's even a degree of evidence that in a few other higher animal species, you can see metagroups forming in other species as well as humans. So there's a human branch and an animal branch to all this. And agro-villages, geopolitical states. And then we've also got the cosmology bit. And like Len, I've been puzzling over that quite a lot, because I think this is where the ecosystem concept comes in, because generally what seems to happen with these jumps is you've got a sort of context which is made up of if you like, an ecosystem of many, many different differentiated systems at each level. And then that ecosystem is what allows something to jump up to the next level. And I suppose I was just wondering whether, since we've talked about squads and military analogies, I wondered whether one way of thinking about breaking of symmetry is when you get a completely new weapon system, like the dreadnought battleship, or I suppose like the nuclear bomb, or like the steel sword. These totally broke what had been symmetrical face-offs between roughly balanced military organizations, and suddenly everything got thrown up in the air. But I'd like to think we can find other examples. So that was as far as I'd got trying to make sense of all this quite a long time ago. And then that didn't work. That works. Okay, so right, forget now about the previous. Right. I'm just using this structure. So I've moved from these these colors having meaning, to these colors just being notional groupings. So the x-axis on the next slide doesn't mean the same as the x-axis on that slide. Now what I'm postulating, and I'm not at all sure that I've got the right understanding of what the isomorphs are, but that doesn't matter if this has helped Len make the innovative jump that we needed to see how to move forward. So my thinking was, right, the impression I got, and I think it's wrong, was that the isomorphs are system behaviors that we should observe in all of these types of system. Now, maybe they're more to do with system life cycle processes than system operational processes, or maybe they're a mix. And kind of I don't care, as long as somebody can get their head around this and work out the simplest possible way of organizing the mapping, so that what comes out of it will improve clarity. So the notion is that, and I've done the other way around than Len was suggesting. What I'm suggesting, because I guess what I'm interested in is, do we see the same isomorphs down here at subatomic levels as we do up here at geopolitical state levels? Or do we see some of the isomorphs everywhere without any particular structuring? Or do we see all of the isomorphs up at the high levels of this complexity, evolution, and fewer of them at lower levels? Or do we see a shift across the spectrum like that? Now, Len has probably got a better feel for the answer than any of the rest of us, but it would be incredibly powerful if we can actually start making definitive statements about this, that either this set of isomorphs you will see in any system, therefore, in fact, they become defining characteristics of systems, and it helps you improve what you define as a system and what you don't. If it's this one, then identifying particular isomorphs of particular types of system will help you make predictions about the potential behavior of that system in situations that haven't yet been explored, or that resulted in total destructions and nobody's able to find out afterwards. If it's really this, then I suspect we'll get a much tighter, a much more exclusive definition of the system. But I've got this question that if this upwards repeating pattern is real, if we lose the link back to quanta, then we've lost this philosophical justification of system realism. So I think my question is, if we tried to do some mapping exercise like this, and I'm not quite sure exactly what the criteria are, but my initial thinking was we just find, in order to break the task down from something that, when I first looked at Len's list of 4,000 papers, I just sort of, God, that's fantastic, and I don't know where to start. So, and if I do start, I could go down a very interesting rabbit hole for the rest of my life and actually not help anybody except me. So this is trying to frame the problem so it can be defined as a team project rather than an individual bit of interest, and in a way that it's forcing questions that, well, already it's made a lot of people think, and hopefully it will. If this is a good approach, then we can actually start improving our understanding of the whole scene and how it fits together, which would be fantastic. I stuck with the grand sequence, I guess, for the reason that Len said, that if you go into the universal sequence of origin in huge detail, the risk is that you'll just keep finding more and more very interesting things that are slightly different, and therefore it's more levels, and there's a risk. I think that's what Alan and Starr said. They say that hierarchy is effectively a continuum for that reason. And so partly for that reason, and partly simply to limit the workload until we've found whether this is going to do whether this is worth pursuing or not. My thinking was you find one canonical example at each level of this. So I'm not sure if this one is an electron or a photon or something else. Nucleon, that can be a proton or a neutron or a proton or a neutron. Nuclei, you probably don't want hydrogen. You probably want something that's got enough structure in it to be interesting. And you might want to look at one radioactive material and one that isn't. Atoms, whatever, and again, you'll get different behaviors in atoms depending on where they are in the periodic table. And molecules, you get very different answers in inorganic, simple inorganic molecules and complex organic molecules. But actually what we're trying to do at the moment is not to do a complete analysis yet, because we don't yet know whether it's feasible. We're trying to scope out the thing by picking one example at each level and then finding out what kind of pattern we get, and that will begin to sketch in what this landscape looks like. If it starts looking like that, then it'd be very interesting to go to one, look at the step from one of these levels to the next, which will have several USSO levels within it, and see whether it continues to look like that, or whether this is sort of a vertical cliff here and then it jumps out to the next one at some level in that. So this is real, my thinking, and I don't know if it makes sense, well, I think it makes sense, but whether it's a good way forward or not, I'm not sure, is that this allows us to dot out, beginning to dot out the landscape to understand the shape of it before we commit into a very detailed, so effectively it's what I would say breadth before depth. Try to scope out the problem before we risk getting dragged into a reductionist amount of detail in what might be too narrow an area. I think, so that was the thinking behind it, and I tried to structure it into, the good thing about writing things down is it forces you to work out whether you understand them or not, and if somebody realizes you don't understand them, then it helps them clarify how to explain it. So I'm delighted that Len has seen how to make use of this to lever onto a further level of understanding. So over to somebody else for any questions.
I want to thank Hilary for explaining those last 3 slides because I didn't understand them before, but he's made it very clear what his block rectangle of blue versus the cloud versus the, what do you call that, parallelogram? Those make it very clear. And they relate very closely to what I was talking about before in this session, and that was that some of the isomorphies have roots in the 1, 2, 3, 4 levels, and those roots and the dissonance change with time, but that doesn't mean they're necessarily different. So the parallelogram is not my approach, nor the cloud. My approach is usually the rectangle, the first one. But my approach doesn't necessarily mean, oh, and then there's this thing. What do you call the cloud I got in? The first one is the rectangle. But what do you call that third one? I don't know.
So the third one, is it a quadrilateral? It's got 4 sides, but it's not. It doesn't have any symmetry. It is in fact broken symmetry.
Well, we'll just call it the quadrilateral, but that's the one where some isomorphies expand, the population of isomorphies expand as you go across the USSO or the grand sequence that Tyler has stated.
It would be very nice if that happens, because that allows you to find a system that you've never categorized and never analyzed before, and just by analyzing this, work out where it has to be in, where it is in this hierarchy.
My experience is the rectangle is not this one. Even with the roots and the dissonance, I still favor the rectangle over the cloud, and I still don't understand the cloud entirely, but
right. The cloud was the only vaguely random shape I could find in the 10 seconds I had to do this. So don't take it badly. I would have done it as a random scatter if I'd had time to generate.
Could be a Swiss cheese, maybe.
Swiss cheese, yes.
Cheese.
Only a French.
Swiss.
Go right to cheese in the French and the Italian.
Well,
so,
we don't have holes in our cheeses.
In France, no, absolutely.
So Hilary presented us with 4 hypotheses to pursue, one, try to falsify and select between the 4. And my experience so far with the very elaborate 50 to 80 levels instead of the dozen that are here. And mind you, I have to say something about that and apologize to you guys. What I'm trying to, and with all of those origins papers and reprints that I have, I'm trying to enable the explanation of the spontaneous arisal of the next emergent level or type of system. Tom Marzolf isn't here, but at least I don't think he is. Tom, are you here? No, Tom, okay. So emergent level of system or scalar level. My experience has been, since I'm comparing all of them and trying to see how one emerges from the other, I have to have the mechanical, and so I have much more detail in my levels. But I appreciate what Tyler and others have done because they have much fewer levels and it's much easier to comprehend or even put on a chart like this. Hilary already said he's confused about the cosmology. My systems allometry study showed that the very small and the very large emerge first in the universe, and then they start to populate other levels going In other words, it's not small to large like the 12 show here at all. It's the largest and the smallest appear first, and then they start to generate new and newer levels as you go interior. So that's how the cosmology fits in with this. And the quanta concerns all the levels as far as I'm concerned. So in any case, I'm taking a different approach, but it won't be finished because I'm not going to live long enough.
That's why we need to spread this out. I mean, I was once doing a sort of review. Shit, I wish I'd published this, because with the benefit of hindsight, I was right. There's some guys working a very big bid for a very big project, and there was 2 people doing the interfaces. This is during the assessment phase. And I said, okay, how long is it taking you to specify each interface? So about 4 weeks. How many interfaces are in the system? I don't know. How many modules are there in the system? About 100. Okay, so you've got 10,000 interfaces to specify, potentially. Okay, 5,000, maybe 1,000. If each one takes 4 weeks, then you're going to take 1,000 months. We haven't got 1,000 months. What are you going to do about it? Which is why we have to do all this boring stuff in systems engineering management. But yes, so that Len, that's why I put the stars kind of co-create with atoms or even nuclei, and then planets co-create with minerals, and where were minerals? So in terms of a in terms of an evolutionary sequence, these guys here need to be way across over here. And then I think there's something that we haven't worked out about ecosystems yet, because you need an extended ecosystem before a new level of complex system can be created within it. And so I guess stars and galaxies are the ecosystems in which atoms and minerals and planets get created. So that's about as far as I got, and then I sort of ran out of steam on this one at the time.
You need a bit of gravity.
Yeah. Okay, so the other question, okay, I mean, I think maybe Tara wants to take over here, because my mental model of all this is that we get, almost all of modern physics has been done since I graduated, and the most modern physicists are even understanding that reductionism doesn't work, and real systems aren't in equilibrium, and all the interesting stuff you need to move away from classical physics to do. So that's really good. But if you think of an electron or something, then all of these other things contain electrons. But does an electron have all the complexities of behavior of a geopolitical state? I think not.
Wait, can you say that again, Hillary? I'm sorry. I was with the question. The question.
Right, sorry, I maybe jumped too far. If we think of a simple quantum, maybe this is a bad example, but my dumb question: if we start with an electron, which is already pretty complex because it's got a wave behavior and a particle behavior, does an electron have as complex a set of behaviors as a geopolitical state does?
Oh, well, I would definitely say no, because the geopolitical state is going to have everything the electron has, because it has electrons in it, and everything that's been added subsequently.
So that's why my expectation was that Len would say it's like this. And that says one possibility, and I'm completely misunderstanding what the isomorphs are about. The other is actually that these here at level 1 are fundamental particles, and you don't have a system generation process to create them that we know of, and that you have to move up there. But in which case, the question is definitely valid of nucleons. We know that nucleons do not have as many dimensions of state space as these guys further up. because that's that's the definition of complexity. How many dimensions of state space are there in the system? But I'm struggling to understand how, if all the complex isomorphies observed up at these levels, do they really go all the way down to here?
So a couple comments.
If they do, that's really interesting, but that's my question.
Right. So a couple comments. One, I wouldn't expect us to be able to say anything about the fundamental quanta, the 12 or 15 things of the standard model at level 1, and until the science comes in and shows them to be components of things. So I mean, I did say that the proton and the neutron are the first system that we know. So that would be, so if the isomorphisms are of known systems, then probably the rectangle has to be moved one up. You know, unless we think we're going to make such a discovery that we're going to be able to projectively go back down to make some guess about everything that all the great physicists in the world are searching for.
Yeah.
the substructures of the fundamental quanta. So then another, so that's comment 1. Good, thank you. Comment 2, lens 7 that he sent out this morning, concrescence, symmetry breaking. I could see his hypothetical stance is this block. I can see why he's saying it is, because he's claiming that there might be isomorphisms that are true at every stage of the unbroken sequence, at every origin. So I could see where Len's saying this. But now we have to, the next question, Hillary, would be then what are these isomorphisms that we're going to be applying to this? I mean, I'm willing to take this as the sort of the beginning, that this would be the grandest finding, right? Like to the extent this is true. Okay, so that's comment 2. Comment 3. This comment would be true of the grand sequence, but would not necessarily be true of Len's unbroken sequence, because at least in this grand sequence, one can say that that the formation of level n, it had to have level n minus 1, all the earlier levels before it, and it created properties that gave rise to the next level. So they all have a kind of a combo. They all have a combogenesis pattern in them. If that's now is combogenesis itself an isomorphism, to the extent that it's similar to that Len's concrescence and George's ontogenesis are in the same category of things, then that would be one isomorphism that would be true at every one of these, at every level. So I think what we would need to do is whether we can agree on some isomorphisms that are true at every level, or some that are, I guess we'd have to get it, Hillary, what you're asking now, we have to get into the devilish details. We have to propose, you know, I like this as an idea, propose isomorphisms, and somebody in the group, you know, make a case for where those isomorphisms exist. I think that would be a really cool project to individual people propose an isomorphism and ask where it exists. So since you've been doing, you're really on board with this idea of the energy, the physical chemistry. Some of them are energy repose systems versus the biological ones that require energy fluxes. Hillary, do you see those different descriptions of stability as being different isomorphisms or not?
Right, that's a very good question, which I was hoping you weren't going to ask straight away. What I was going to say about that, though, and maybe there's something that has been eating away at me for quite a long time, and maybe what you've just said is the answer to that. That the energy, right, according to Carlo Rovelli and his view of quantum gravity, time doesn't exist down at these levels. And the conclusion the hypothesis I formed reading his book is that, right, time is closely linked to entropy. You can determine the direction of time by decay, by increase in entropy. Entropy is a property of multi-level systems. You don't have any entropy in a neutron. It'll carry on forever unless it gets hit by another neutron. So you suddenly have a process that denotes the end of one time period and beginning of another. And atoms, once they've reached their ground state, do not further decay on their own if they're left to themselves.
Right.
Whereas a cell, an organic, unstable large molecules, I don't know what their stability criteria are, but cells will die once they stop getting enough food, or when they get equivalent of cancer, when they just sort of reach the ends of the line. I guess they divide. But if you deny them continuous supplies of energy and continuous supplies of this, that, and the other, take them out of a sustaining environment, and they'll die. And that's not true of these guys down here. So it seems to me there's something happening there, and then there's something about well, okay, let's concentrate on that one, because
let's just concentrate on that one. Because we can talk about it pretty clearly.
Yes.
I think that we take a look at the universe as it exists now, and all of these models right now are based on what it is now. If it started with a big bang, there was a set of conditions which were quite different before quarks could even get together and form protons, neutrons, and so forth. So there was, in the life history of those things, a process, right? And so that implies time. The fact that they are stable as the universe cools, they become stable in that configuration as the universe cools, may say that, well, time has come to a stop for them, right? But there was a point in their life, if you will, where there was a sense of time. There was a process going. So what I wanted to point out was I've got a very simple ontology. And that is that at every one of these levels, and that's why I loved combogenesis, because it spoke to that. At every one of those levels, you've got individual things that have, I call it personalities. But basically it comes down to either tendencies to attract or tendencies to repel. And between that and the mixing up, I'm glad, Len, that I saw the statistical mechanics or thermodynamics part of it, because everything's being constantly mixed until you get gravity pulling stars together, in which you then get a directed or broadcast flow of energy out into space and bathing the planets, right? So the simple idea that, pardon me, nucleons, either protons would push apart unless there's a neutron to mediate, and that electrons and protons attract one another because of electric charge, and on and on. But as you go up, what happens? So that takes care of the atoms. What happens at the molecular? Well, it's basically a repeat of the formation of atoms, but now we've got geometry involved. There's going to be different shapes. Same thing for crystals, minerals. Same thing basically for organic molecules. There are the electrostatic, electronic, all these different kinds of things that bring them together because we're constantly mixing and making opportunities for things to happen. Viruses, I don't know about viruses. What I learned about viruses is that they were degenerate forms of life, that they weren't really something put together unless there's some newer ideas that have come about. But the transition from organic molecules to protocells and so forth, I think that's an important part to put in, and that's what I would put in place of viruses, protocells. But in all these cases, you see the same thing. Now it goes into the area of what we would normally think of as signaling, that basically the attraction or the repulsion is based upon the ability of that unit to receive and transmit signals to each other. But it's fundamentally the same thing. There's attraction, repulsion of unitary things that then lead to that. And that's what I've been calling auto-organization in replacement for self-organization. And that's fundamentally it. In my view, those are the things that you can trace all the way up. That coming together, then, and the environment that tests whether or not something is going to be stable or not. Like going all the way back down to protons and neutrons, it was the environment under which they were created that also was changing. It was cooling and deciding, and that would test. So in the quarks, for example, you've actually got 3 families of quarks, but the vast majority of matter that we know about is comprised of just the up and down quarks, I think it is. What happened to the other ones? We can recreate them in very extreme conditions, in colliders, I guess. But they are, they're not, maybe in stars, they're still being created. But the idea is that the universe has changed dramatically since the time they were first produced. So that environment, for me, is always the key that is testing. So energy repose is basically just what happens when the universe cools sufficiently after the Big Bang. Yeah, I've talked enough. Anyway, that's my simple ontology.
So George is proposing.
Go ahead, Tyler.
So George, you're proposing attraction and repulsion as isomorphisms that are occurring on all levels, which might have some relationship to Len's counter-parity. I don't know. We'd have to go into that. But my question to you, George, is: do you mean literally attraction and repulsion in the way physicists talk about it, or are you broadening those terms to mean processes toward integration and versus processes of segregate of individuation and continued segregation? I didn't know whether you're meaning literally attraction, repulsion, or using them at different scales to mean different kinds of processes.
Well, on the surface, they'll appear to be different kinds of processes, but why do cells interact with one another? Right? And they're doing it because at the base level, they're organic chemistry and biochemistry, and chemistry ultimately does depend upon attraction and repulsion. So,
Oh,
what,
you do literally mean that, because I was saying
well,
the cells
I
are
mean,
responding. I mean, you brought in cells are responding to other cells
right.
as whole things, and so some of
Now,
them are
what I'm saying is it ultimately gets down to that fundamental electric force, attraction and repulsion, at least from the point of atoms on up. But it is mediated through different things. I very firmly started with the commitment, the ontological commitments of there's matter, energy, information, and knowledge that the universe is made of. So it's those interactions.
See, I guess I can't. I mean, I've thought about that. Is ultimately every interaction, every relationship comes down to attraction, repulsion of electric forces or gravity, or this is or the four fundamental forces of physicists. But I find I can't figure out if a bird sees another bird and wants to mate, or sees another bird and it's a bird of prey and needs to escape. I mean, that's kind of an attraction and repulsion on a biological, ecological thing, but it's not because of positive and negative electric charge.
Let me try it again. I'm not saying it's because of the charges. What I am saying is that ultimately they've evolved behaviors to be attracted or be repulsed on the basis of signals that they're receiving and processing. But ultimately, it's because of those fundamental attractions and repulsions. So it's a buildup, and as you get more complex, you get more, sort of attraction at a distance or repulsion at a distance. But it's still attraction and repulsion. So no, I'm not saying it's electronic among the birds.
Okay. Okay.
So you're saying that the behavior is attraction or repulsion, and it's caused by different mechanisms at different levels.
Yeah, and I was just trying to make a case for once you get to life, it looks like it's happening differently, but life is ultimately based on the chemistry, and the chemistry is based on the those four forces. Well, three of the four forces.
Earth, fire, and water.
Huh?
Sorry. I said earth, air, fire, and water, and then I apologize.
So anyway, I'm just trying to emphasize that I see the what is to me isomorphic across all these levels is this notion that concrescence or auto-organization happens because of attraction. And then once that is done, it has to be tested against the background of the ambient conditions. I used the term selection for that. But at the same time, there's repulsions going on that keeps this mixing working.
Gary, it's been an hour and a half, and my son is just over to visit because of the pandemic. I only see him once every month or so. So I'm going to go down, or I won't get breakfast, I'm told.
Okay, no thanks, Len. No,
so I have
that.
to sign off, you guys. Please do see the response I made to Hillary, and maybe respond to it, okay? Sorry that I have to leave you. Bye.
No, thank you. Okay. Have a nice day, Len.
Len.
Well, I'm sorry that Len left, because George, I have asked Len annually, probably for 20 years, in an email, hey, what about attraction and repulsion? And is that counterparity? Is that what you mean? And I want to see, okay, then and then I go through the isomorphies, which I have lists of, by the way, and I hold his feet to the fire and I say, okay, are these incidences of, do they not exist? Come on. or are they features and functions of another isomorphy? And I try to put his feet to the fire, and I don't get it back. So I decided, you know, pretty much to blow him off and include it as an isomorphy myself.
Oh, good.
Which makes it difficult because I'm putting together this field guide, and I'm putting together features and functions of about 12 different isomorphies, and then I'm listing kind of in a glossary kind of form some a whole bunch of isomorphies that are more, you know, they're all isomorphies within isomorphies, and some I don't need to go into so much detail for just somebody who, I just need kind of a glossary. But because, you know, when we talk about most of these things, it's in our common language, a lot of it. It's how we're thinking already, because it's what we're made of. So as I'm writing this, I'm running into these issues. And so I took pretty close notes, even though it's going to come up on the, and I have notes already on your whole thing, George. I took my own notes on your ontology. This was the most concise overview of your ontology I've had yet. The pulling out the matter, energy, info, knowledge structure that you've put together is really important to me. It really, I had a hard time writing about information. I was able to do it, but I wasn't. It's easy to write about information theory and what Shannon did and what all these different people have done. It's very different to put it in as an isomorphy, as the thing that actually forms things. You know, it's very different. It's very different to write about chaos and not write about chaos theory. It's really easy to write a history of chaos theory. It's another thing to write about chaos. What is it? How do you break it down? What actually is it? So it's really easy to write about off the top of your head about this is the way something is according to somebody's history or opinion. It's another thing to break something down and actually define it and give examples of it and put your feet to the fire and say, this is, as you guys know, when you write it, you got to back it up. And so as I'm listening to everybody, you know, like when my first question was about bifurcation. And because, okay, one thing that happens as I'm writing, and I've known this before, when you study one isomorphy, the whole world is that isomorphy, you know. Forrester, the whole world is feedback. You know, that's what systems are. And everything else doesn't even matter. That's the central everything. Well, this week it's been self-organized criticality and bifurcation. And bifurcation isn't necessarily in self-organized criticality. This guy Bach, who wrote about self-organized criticality, doesn't include bifurcation, where catastrophe theory is bifurcation theory, and chaos theory, bifurcation is part of chaos theory. So, but self-organized criticality says, no, you don't need that because there's cellular automata show that we don't even need that. The cascade can happen without bifurcations. And then out comes a 2019 article about showing how sand piles show bifurcations because they're avalanching and smoothing is actually a bifurcation process. So I'm sitting here going, all right. So Len outlines its counterparity, broken symmetry, central stability, peripheral instability, concrescence. And I'm going, it looks like self-organized criticality to me. It looks like, you know, I start going fancy names for stuff that I've been reading about. So I'm more able to pick out you know, then I look at auto-organization, self-organization, and the tendency to attract and repel. You know, again, how does that fit into Len's peripheral instability, central stability? You know, concrescence, steps to emergence, looks suspiciously like auto-organization, self-organization processes generally, so when I start to break down and actually look at the features and the functions and the mathematics, the modeling behind these things, then I question those defining words. Do you know what I mean? It's just that's where I'm at.
A thought occurred to me that we're using the term isomorphies. And I wonder if well, here's what I mean by the use of the concept of isomorphy. We're looking for what is isomorphic from just above quanta all the way up. What is isomorphic? And so some processes, because we're talking about change, things have to change. And so some processes, like Len's concrescence and my auto-organization, Tyler's combogenesis, coming together. But at the same time, not everything can come together. Some things have to spread apart. So that change is what's isomorphic on all those levels. And you find different mechanisms involved in it, but it's still, that's what's isomorphic. Len started out with system process theory, as I understand it. And he looked at all these processes. And I went back, by the way, been reading Bertalanffy's book again, for the umpteenth time, and paying particular attention to how he uses isomorphy. And he's basically saying it the same way I've been thinking about it, and I must have gotten it from him, is that there are certain things, certain processes that we will find isomorphically across the different disciplines. Pardon me. So anyway, that might be a useful way to think about it. Instead of thinking in terms of what are these isomorphies, think about what is isomorphic as we go through these levels.
Well, Len himself was surprised when he realized he himself changed somewhere along the line for labeling, went from isomorphic to isomorphies. I go crazy because I'd call them isomorphs. I'm a writer. I'm like, isomorphies. I go, let's call them isomorphs. And they are the same as what he calls systems processes. They're the same thing. And they're the same forms found throughout nature. And if they aren't found throughout nature, then they aren't isomorphs. You know, they aren't systems processes by definition. So the definition, they're all candidates isomorphs or candidate systems processes, because they have to be shown to be throughout all systems, because that's what makes them a systems process. And that's the basic thing behind his thinking. I know that. And so, yes, and then there are patterns within the patterns, you know, like as George was saying, auto-organization is made up of different patterns or isomorphs. You know, oscillations are made up of feedbacks, you know, they're all interacting. They're networks of systems processes. Their isomorphies make up everything.
Yeah, so the problem is really finding the sort of minimum orthogonal set from which all the others can be constructed.
Yeah, if you can do that.
Yeah.
Yeah, there are about, like I said, and when I'm writing, I'm using about 12 basic ones. And Len and his, I'm going to use a couple different now, but in his ISGE is Integrated Systems General Education Science course that he put together. It's a 2-year basic science education course that he structured and taught, teaching these basic science from the views of hierarchies, networks, feedback, and he covered all the basic sciences I think he was doing it for nursing students and undergrads. Nobody else could teach the class because you had to have a good enough background in all those sciences to teach. Couldn't carry out. I mean, who could you hire to teach that course? But he did cover he used about 12 systems processes. And those are the ones that I'm using in my book as the basic ones, and they are made up of other processes. But if you understand those, and most people already have a handle on what networks are and hierarchies are. Feedback now, that's a really messed up, commonly used word that isn't quite understood. Yeah, but it's interesting. I think.
So Lynn, chaos is. I'm just gonna, since you're suggesting these are going to be on the level of what George is proposing or talking about, the attraction repulsion, properly explained that it's on different scales, and I do agree with that whole approach of that there's something maybe large called attraction repulsion that manifests in various specific ways, but on some bigger scale, there's something there that's an isomorph that's really important. So my question is chaos one of the ones that you're using? Because I'm seeing that appear in some of these lists, like hierarchy. Is chaos one?
Chaos is really tricky because, and I'm at the end of writing about it. I'm getting tired of it.
But it is one.
Chaos theory is, I'm writing, chaos theory kind of lumps together a bunch of things, a bunch of processes. It lumps together, chaos theory itself lumps together bifurcations, chaos, emergence, fractals, all kinds of things within.
But you said chaos is different from chaos theory. So when I read the word chaos and you said it's an isomorph, I was thinking that is when George is talking about the sort of the bumping around of things.
Yeah.
Whether it's cells in the ocean or whether it's animals, a wildebeest herd, or human nations, that the sort of the bumping that's going on, but that's not the isomorph you're talking about when you use the word chaos. Okay.
Chaos gets messy, but chaos is the messy part before emergence.
Yeah.
And self-criticality, people don't recognize necessarily that chaos has to happen before emergence. And so out there's a lot of disagreement about what happens before the emergence of new things. And now there are people who are showing statistically that chaos is happening. We know it happens in phase transitions after the bifurcation and the breaking up and then the coming together. So as I'm looking and I'm listening to George, and I'm listening to Len describing and you guys describing your ontologies and, combogenesis and all of that, sounds like chaos theory to me.
Well, I want to go back just for a second to Hillary. I was going to ask you, Lynn, about hierarchy and networks, but Hillary, I think this is all within this proposal you're making of a program of people maybe making proposals within this group for universal isomorphs and trying to make a case and then see what the other people think. That's kind of what we're starting to do here. I mean, I asked Lynn, not Lynn, sorry, I just misspoke. I asked Len today about the symmetry breaking that he was proposing as something that was true in all his unbroken series of origins, which is between 40 and 50. You know, and I'm sorry he's not here. I would say, you know, and he kind of hand waved on it. He said, "Gosh, I read some paper about symmetry breaking." So you know, he didn't make a very good case for that at all.
You know, that was a central feature in Smith and Morowitz's book.
Oh, wow.
Symmetry breaking is covered there, as is phase transition. And I'm sort of still maintaining that the levels that you show, Tyler, what we see, what the difference is, there are these micro examples of things, but what we're seeing is essentially the result of a phase transition. That we go from one global state of matter to a new global state of matter at a new level of complexity.
So George, if we go, let's take something we all will understand, or it's biological, going from animals to animal social groups. Sponges were living pretty much by themselves in the ocean. At some point when animals became mobile, it became advantageous in certain situations, not all, for some animals to form groups and have group behavior. Now, some of what I heard Len say was that if he defined symmetry breaking as leaving behind something, then I totally agree with that. If that's how symmetry breaking is defined, is what was left behind as the new thing happened. So what was left behind when animal social groups formed? Some animals in social groups. I'm sorry for this. Some of the animals in social groups can no longer live alone. Okay, so ants or bees in colonies can no longer live alone. But do we want to call that? So I'm willing to entertain this idea that we want to call that symmetry breaking, but we might want to call it things that are lost.
Yeah. I have a lot of trouble with words that are used that sound really profound, but the user may not know. I said this before, didn't I? That that word you're using, I do not think it means what you think it means. And so concrescence, I still have a lot of trouble with that because it's a word that's used in a very particular set of circumstances. I ran into it in embryology, but it's hard. How are you going to get that across to the common person? You know, what concrescence is. Symmetry breaking, I think, is along the same lines. There's a very, very definite physical definition of symmetry breaking. It's very clear, which had to do with the four forces separating. You described that very well. I've seen it used in other circumstances, but I'm not convinced it's really a good way to go about it. So I agree with you that it would probably be better to describe the phenomena, the phenomenology of it, rather than try to, you know, encapsulate it in a word that not everybody's going to agree on the definition. So anyway.
Yeah,
That's
I drive people like Gary mad in systems engineering projects by refusing to pin down terminology until we've understood the concept. It's often made me unpopular, but I prefer that because in the long run, everybody knows what they're talking about. Yeah, I was going to, while folk were talking, I was thinking about how do we simplify the problem. And actually, we don't need to do all 12. We only need to do 3. Maybe a nucleus, maybe the eukaryotic blank cell, and for example, an agrovillage. And if we use those to start mapping the isomorphs, you find all of them or some of them in these 3 example systems. That's going to give us a very quick feel, first of all, for what we're actually trying to do, and second, for whether it's a rectangle or whether it's something else. So
well, I've been working on a set of webinars recently, and it's been taking a lot of my time. But I think I'm pretty close to finishing that up. So I would take the 12 levels and see if what I can define as attraction and repulsion.
Yeah. Okay. Yeah.
At every one of those levels.
Good.
Yeah, that would be great, George. Make a case for that. Yes, that would be great.
Yeah.
Okay.
And, yep. Mm-hmm. Mm-hmm.
Hmm. The other thing I'm wondering, Len, is in terms of Len's isomorphs or isomorphies. coming back to that diagram I was showing earlier. If I might show it again. Is it worth also trying to categorize Len's isomorphies in terms of where they fit across this functional chain or this process chain? So, I think, as Len said, we've got isomorphies of pathology and sustainment, which are to do with this peak, where the thing exists, the system exists. Yeah, we've got isomorphies of emergence, which lead to this, and we got isomorphs of diversification. So this is the spreading out, I think, within the level. And where does chaos fit? And I was wondering, is chaos coming down to here? The isomorphies of possibility. I don't know, but is it worth taking a look at the current set of isomorphies and seeing how they fit across this?
The only problem that I have with this, I've tried to wrap my head around it several different times, and I'm still not quite clear on it. And that is, when we see this at the top of a waveform, we see this process of concrescence, things coming together.
That's fair, I think.
What we don't see is that some things come together for a short period of time and then split apart again because they're not really compatible, or their combination does not bear a benefit for them surviving in whatever environment we're talking about. So to me, there's a lot left out of this. And really, maybe throw out the word isomorphs here, Gary, because they're really processes.
Yes. The other interesting thing is, how long does a thing have to be in existence for it to be considered a system? If you have a system which exists for a nanosecond, is that not still a system?
Well, it might be a system, but we, from our perspective and understanding, we're going to have something that lasts a little bit longer, I think. It's
Hi, Tom.
Hey, Tom. Hello. Yeah, it's. I mean, that's a good point, but we do see protons, at least as of right now, they're thought to be immortal.
Yeah.
Or at least there's a good case for them being immortal.
Yeah.
Whereas, individuals, I mean, we're attracted to one another. In our case, we're forming this, what do you call it?
System.
Well, it is a system. It's becoming a system. But we were attracted by the notion that we all share this idea that, we want to work possible. Out. Anyhow, yeah, I'm just in. The other thing that was a little off-putting, I've mentioned it to Len before, but rather than have a waveform, I understand what he's trying to get at, that there's sort of two polar aspects, but the waveform suggests that this is happening on sort of a regular basis. And I don't know if you guys remember my diagram, which was in 3 different things. I'm showing a lot of stuff going on in parallel at a lot of different levels, which does address the ecosystem question. So anyway, I mean, I think Len's really got some very, very valuable stuff, and I'm hoping I can understand it well enough. But the way it's being expressed right now is still giving me a little bit of difficulty.
I want to, a general comment is that in Len's parlance, isomorphies are systems processes. And systems processes are isomorphies. And all is process.
Yeah.
All.
No, I think that's right. I think it's phenomenologically true that all is process. Every system is a process, and every process is a system.
And a set of processes within processes.
Right.
Yeah.
Right.
Networks of systems processes. Yeah.
But using the terms interchangeably,
it's confusing.
Raises some I think some problems. If they're processes, call them processes.
I'm calling the whole, in mine, I'm avoiding isomorphies. It's too confusing.
I think
systems processes. My book's so basic, I cannot be confusing people with terminology like that. I mean, I have to get really basic.
Right.
As a writing challenge, I can't be fooling around with that kind of terminology. Yeah,
the thing, that's what I was getting at before. What we're looking at is what of those processes we can identify in all of those levels. So then that then means they're isomorphic.
Exactly. Right. They're the same form showing up at each level. Exactly. And that's going back to Burton Lanthey. And that's where Len came out of. He came out of all that. And he took off from there going, okay, it's not just feedback, the first one that everybody identified. And he was with all those people as they were talking, right? Way back there. And then he started going off into his own world, reading Science and Nature every week and underlying, oh, these must be processes because I see them everywhere. And then he grew it, literally organically grew it for decades. So we're talking to somebody who's got this decades of this kind of, incredible database going on in his head. And so when I try to nail him down, it's often not, he has a feel for something based on a lot of experience. But sometimes he's just plain wrong.
Not in his humble opinion.
Yeah, but I catch him, and I just say, or he'll turn around and say, I'll ask him, say, okay, I want you to get specific about this because I need to quote you on this or consider this. And then he'll say, no, that's not true. And then I'll read another paper of his that says it is true. However, I'm not dissing him.
Yeah, no.
Yeah, and keep in mind it's being recorded.
Well, that's fine. Like I said, I keep meaning to.
This is a huge compliment. This man is an incredible body of knowledge and work.
The thing that I've been troubled by every time I look at the list of system processes, the analogy I would draw is with the systems thinking or system dynamic archetypes, where you can pretty much describe any system dynamics with a few elements, but there's these repeating patterns that come in. There's about 12 or 15 of them, which are about they're kind of like the molecules. I guess if the individual elements in the models are like atoms, the system dynamic archetypes are like simple molecules that you can combine into more complex molecules, more complex patterns. But there's only about 12 or 15 of them. And I suspect that if one analyzed the system process isomorphs, archetypes, whatever you want to call them, maybe archetype would be a good word to use because it gets into that way of thinking. I think that we'd find that some of them are at different levels. In other words, that some of the more complex ones can be decomposed into simpler ones. I don't know. But if they can be, then we need to work down to the most useful, simpler layer.
Yeah.
Well, that's been my whole thesis.
Sorry?
That's been my whole thesis. I've got a whole part of the book that's on model archetypes for complex, adaptive, and evolvable systems.
Yeah.
But they break down into simpler systems.
Yeah.
I really like using just systems processes generally. That they consist of other systems processes. When you can't describe one systems process without describing others. So as I'm describing, like in the field guide, as I'm describing a network, I'm also describing interactions or bonds, which are links, bonds or links. So every time I'm describing it, I've put, when I'm describing something, you might not even recognize it as a systems process because we take it for granted as this is what something is. So I've put it in bold. It'll probably be linked to a definition or the page on that describing that systems process. It's one of the problems out there that I run into is systems processes like hierarchy should be hierarching. Networks are constantly forming, if we could call them networking, it's networking.
Yes.
We're constantly, some words work very well, like we're constantly developing and evolving. Works very nicely because they're set up as process words. They're seen as process words. Anything that ends with TION works very nicely. Bonds, bonding, boundaries, bounding, some of the words work very nicely as a gerund or that show that it's an activity, a process, not just a thing. And it gets very Buddhist because we start talking about it's instead of things, about all is change.
From a process perspective,
yeah,
would the largest process be the expansion and cooling of the universe? Everything else is subordinate to that.
So it's because George has this equation for I guess you 8 parts, eight things that you look at in systems. Hillary's now got, I don't know, Hillary, you're 12 to 15. Maybe it's on some of the PowerPoint slides.
Sorry, what I was talking about there, do you know Jay Forrester, Donella Meadows' system dynamics stuff?
No, I mean, I know who Forrester is, but I haven't read him.
Okay, so it's more a systems thinking tool than a real systems
properties, not properties of systems. Then it's
a very simplified view of system properties. So I was using it as an analogy for it to be nice to get to, not because I think they're necessarily important. Archetypes like success to the successful and the problem with symptomatic solutions and stuff like that. Yes, it's very much in the systems thinking world rather than systems science and engineering world. So I assumed everyone would be familiar with them, but forget it.
But still, we're getting different angles on this question of universals. I think it's really interesting.
I have to bail out in 2 or 3 minutes.
Yeah. So any final words, Hillary?
No, I think that's been very good. I'm glad I had that random thought yesterday and decided to do something about it. It seems to have been worthwhile. But yes, I mean, I think if George can do this example he's already got in his head of one or two things going all the way up and down, then that'd be it'd be better to just take each isomorph and try to map it to every level. I'm not sufficiently familiar with what the isomorphs are actually to propose that. So maybe if 2 or 3 people could get started and then we see what it looks like.
Yeah,
I think that'd be fabulous.
yeah. I think there might also be some mileage.
Len wants to say something.
Sorry.
Oh, yeah.
No, go ahead.
I was just interested in, when you're doing this, I'm very interested in the process that you use to do this. So how do you look?
Yeah.
What do you look for? How do you compare if you're a group of 2 or 3 people? How do you settle, or how do you model differently? I think this is what, yeah, this is the angle that I'd like to work on, and it's very difficult to capture actually, because it's in the moment, it's in the discussions. People are saying, well, we won't be able to do this because we all have a different definition of this, or we all have a different representation of this. Or so either we abandon because there's no agreement reached, or we kind of settle on some not so explicitly defined definition that we all see, differently, but it works. But I think that if we developed a way of a method to compare, to capture, to contrast, to document, maybe we would move forward quicker than we think, rather than saying, well, let's capture it and get it and agree. Maybe it's worth saying, well, let's get the half-baked thing but document it, because the documented part of it is going to evolve and reach some stability at some point, some form of meta equilibrium. I forgot the name. Meta stabilization. So yeah, that's my. If you wanted to do that, I'd be interested.
Well, you can continue a role of observer, can't you? So
Yeah.
what it is that we
But it's actually what I end up thinking that I'm doing is trying to develop some observational, some cross or co-observational methods, or co-modeling methods, or co-stabilization methods, in order to, let's say, prepare or orient towards the emergence of some integration, which needs to be undertaken in parallel of actually integrating and getting some maybe temporary agreement on something that can evolve. But if we orient the way of doing the thing and documenting it in a way where we can continue to improve the integration, I think we will have progressed.
I have a suggestion. We could compare, because you're right. What we could do is, because that's what I tried to do when I compared the 3 theories, combogenesis, ontogenesis, and whatever lens is called, USO. I think it would be interesting to take Len actually has a systems processes theory set of hypotheses, by the way. There are about 20 hypotheses. And I have them on I could ask permission from him. I don't know if they're published anywhere. They might be in the systems
Did he not share them?
But I've got
I
them. Yeah.
I
can
don't
share-
remember. My head is.
that's okay, I could share those. It's no problem. And then I'd like to compare those to George's 8. 8, you know, George, your 8 main ideas, or what do you call them?
Well,
And-
those are abstract symbols representing things that you would actually find in systems.
Right.
The process is assumed. That is to say, the dynamics of how those 8 things, well, one of them is a time constant, so the other 7, how they interact with one another in an ongoing fashion.
Well, it'd be interesting to look at yours and contrast it with those hypotheses and see how they compare, just generally, in the way that you're talking right now.
Send me the hypotheses and I'll take a look at it and see if
it's very different. They're very different. It's almost hard to compare, you know, but I'm just comparing and contrasting maybe, but I will.
Okay.
Right. Okay. Anyone else? Something to say before we wrap up?
I need another cup of coffee.
I need beer.
What did you say? You said you need a beer?
I need a beer to wash all of this away now.
It depends on your time zone.
Yeah. Well,
Yeah, I'm even later than that. I need a glass of wine for dinner.
I'm thinking about crawling back into bed.
Yeah.
Probably.
That's right. That's right.
Okay.
Yeah. I've been sleeping most of
Anyone
Well-
else? Last words?
Just good talk. Thanks.
Okay, thank you. I have recorded it. I'll post it up.
Yeah, thanks.
Okay.
Great
Take
conversation.
care, everybody. Thank you.
Thank
Bye-bye.
you.
Right. Bye bye.
Bye-bye.